Hello, my name is Kale Warner, and I will be presenting Maxwell's wave equations. Though first we might want to ask ourselves, what is a wave? A wave is the transport of energy without the transport of matter. To see what this means, let's first consider a surface at rest. Next, let's consider a surface in motion. For a surface in motion, the same point is modeled for each moment of time. However, over time, its position or change in the z latitude or altitude changes over time. If we consider an added dimension, say in the x direction, we see a wave form over the two dimensions, and first we see a 2D wave in time and space, although it appears 3D because the time axis is our third dimension. Now, although a surface displacement is shown here and changes in direction, not direction, but more the displacement of a, per se, space, similar measurements can be made on electric and magnetic fields using Maxwell's equations, Ampere's law, and Faraday's law. We notice these expressions are written in time domain form. They may also be written in frequency domain form, where J is conduction current density and omega is angular frequency. Also, the expressions on the right can be noted as their time harmonic Maxwell's equations. Now, taking the original wave of the surface that we had investigated earlier and thinking instead in terms of our electric and magnetic fields, we can obtain a similar linear or planar wave from the following derivation, where the electric and magnetic field intensities are mutually perpendicular and the propagation vector is orthogonal to both. The propagation vector is also called the wave vector and is denoted by k hat. Now, what if we were to take the curl of each side of each equation, both Ampere's law and Faraday's law, taking first the curl of Ampere's law and denoting the current density of the conduction or conductivity multiplied by the electric field, we obtain the following expression. On the left-hand side of this equation, we actually have a vector identity, where the first term of this vector identity is actually equal to 0, since the divergence of any solenoidal field is 0. Oh, and that is a 0 vector. Therefore, the next step in our derivation will be that the negative Laplacian of the magnetic field intensity is equal to the curl of the electric field derivative and also conductivity term. We carry through with the curl on the right-hand side of the equation and see what we come out with. It appears that Faraday's law is embedded within this equation as well as its first derivative. Bringing these over to the left side of the equation reveals a wave equation in standard form. This is our first wave equation. You may be thinking to yourself at this time, wow, I really don't want to solve that. That's okay, we're going to write it in time harmonic form and it's going to be a lot easier. Now, writing the expression in time harmonic form, we simply recognize that the derivative of the variable h is simply the multiplication by the angular frequency and a term j, the imaginary number, or square root of -1. Note that this simplification can only be performed if we are accurately able to assume that our field is sinusoidal. If not, we will have to resort to using wave equation 1. But here's wave equation 2 written in time harmonic form. In this final expression, wave equation 2, we make the following assumptions. Firstly, that the h field is actually a phasor, where the wave vector k is also written as a beta vector, which is also the wave vector. Now, another important distinction that we have to make is that we are in the frequency domain. This requires that we use a sinusoidal function, or a periodic function of some frequency that we can define in angular terms. It is also important to possibly look at the intricacies of the two terms that we converted into the frequency domain. So let's look at the first term. For the first term, we first performed first derivative, and we obtain j omega, and then we perform the second derivative and received a coefficient term of negative omega squared, which cancels the previous negative term here and makes it positive instead. Though for the second term, we see that only one derivative occurs, and therefore we have multiplication by j omega. Since we factored out an omega squared, it is instead divided by omega, so that the net multiplication is by omega. Also notice here that we forgot epsilon. We forgot the epsilon or permittivity value in the denominator. So just remember to always double check these equations. We also forgot to mention that this is a phase, or up here the H field. That's just a minor modification I made. Now that we've derived the wave equation for the magnetic field, let's consider the electric field. We're going to skip some of the steps that we mentioned earlier, since we make the similar substitutions. Now instead we have the curl of the magnetic field intensity embedded in the time derivative of Faraday's law with curled, and so what we have is Ampere's law embedded in that time derivative. So we substitute Ampere's law, and with a couple more steps we notice a very similar result to wave equation 1 in our wave equation 3. Let's return to our wave equation 3 and make this small comparison. Sorry, I mean to say wave equation 1. Here in wave equation 1, we see that the first term is subtracted, multiplied by permittivity and permeability, and then the second term is subtracted, multiplied by conductivity and permeability. Both terms are linear, and we see that we have the second derivative before the first derivative. Now let's go down to wave equation 3. In wave equation 3, we see the same result. The first term is multiplied by permeability and permittivity, while the second term is multiplied by conductivity and permeability. And the first term is the second derivative, while the second term is the first derivative. Now, when we transfer this into time harmonic form, we also achieve a very similar looking wave equation 4 to wave equation 2, again in phasor form. Now if we consider these wave equations, how do we really analyze the fields from them? This is probably one of the greatest questions with wave equations. For this discussion, we will merely look at the time harmonic forms of the wave equations to derive what possible changes in the electric and magnetic fields can occur with things such as permeability, permittivity, and conductivity. I think the biggest question now would be also, what is the wave vector? What is the propagation vector? So to define the wave vector, we look at the direction of the wave. Since these are plane wave solutions, we've assumed that there is no change along the plane of propagation. Therefore, any modification to the electric or magnetic field components would occur along their direction of the vector. So if we consider that this term here in front of each of the H and the magnetic and electric fields as modifying them in the direction of propagation, we would consider the propagation vector as probably being something related to those coefficients. However, we must note that the propagation vector itself is orthogonal to the field components and does not modify them in that vector direction. The definition of the wave vector is the actual wavelength divided by 2 pi, and its direction k hat is defined by the pointing vector, which is given in another lecture video, where we have the electric field intensity crossed by the magnetic field intensity directions to define the direction of the wave unit vector. Therefore, if the electric and magnetic fields are not perpendicular, then we can still have a wave equation. However, if they were parallel for any case, then we may obtain a propagation vector that is 0, in which case the fields do not exist. So considering this, we do note that there's still this coefficient term, and so what physicists have done is that they've found that the wavelength divided by 2 pi is equal to the wave vector term, which is the square root of that coefficient term. Therefore, it can be dependent on the permittivity, permeability, and conductivity, as well as the frequency. So it can become quite complicated. So there's been simplified terms that they've used for actually dealing with this wave vector. First, we consider what happens when an electric field enters a good conductor. In a good conductor, we assume that the conductivity sigma is much greater than the permittivity multiplied by the angular frequency. The permittivity multiplied by the angular frequency is related to the dielectric loss of the material, and there are many other models that describe this, which can be seen in other videos. However, we're going to first just consider that sigma is much greater than epsilon times omega. The result is that the second term within the brackets inside the radical expression becomes much larger than 1, and therefore we have 1 just simply disappears. We have a cancellation of terms in the numerator and denominator, and the final expression comes out as. Pardon the mistakes in the numerator before. There are some terms in the denominator here which actually jump to the numerator. So now this is our final expression here, this last equation. We'll notice that there's this negative imaginary number inside the radical, which is hard to work with. So let's consider that it as the Euler's number, or should I say in polar form. So we have e to the negative j pi over 2, which is equal to negative j from this Euler's identity. So from this identity, we can also find out that if we take the negative j pi over 2 and divide by 2, now substituting out this expression in for the square root of negative j, we obtain an expression for the wave vector of a good conductor. Where this is here is the final expression for that. Now, if we also consider not just a good conductor, but other materials such as, for example, a dielectric, we have two terms that we can break our wave vector into. We have alpha and beta, where alpha is the attenuation coefficient and beta is the propagation coefficient. Alpha is measured in Nepers per meter, while beta is measured in radians per meter. Although the derivations of these two terms is interesting, it's, I do not believe, required for the course, therefore I will simply summarize them below. We obtain two very similar looking terms, with the one difference being -1 and +1. Now these are pretty complicated expressions, therefore we often make an approximation for a good dielectric. So using the binomial approximation, as we take the limit of our conductivity divided by our dielectric loss squared, as it becomes much greater than 1, we can say that 1 plus n to the power of 1/2 is equal to 1 plus 1/2 n, and therefore the 1 and the negative 1 in the parentheses they cancel, and therefore we obtain the following result. And that's for a good dielectric. For a good dielectric, we can also assume that beta has the same propagation coefficient as in free space, but also accounting for the index of refraction of the dielectric material. Therefore, we obtain the following. Now let's consider how these fit into an expression for an electric or magnetic field. First, for an electric field, we notice that it attenuates within a conductor as free charges on the outer surface of the conductor tend to move around, so that we have free electrons, and as the frequency increases they become closer to the surface, an effect known as the skin effect. The distance of this is denoted by delta, and the skin effect can be given as 1 over alpha. And for a good conductor, this 1 over alpha skin depth would be either of these two expressions. Now another possibility is also, that the skin depth is actually 1 over the Euler's number, or the time constant of the propagation. So it's within a wavelength of the incident electromagnetic fields. To see the effect of the complex wave vector's effect on electric and magnetic fields, we simply substitute it into the original expression, or the definition of the phasor form, and then convert that to the time form. Note the mistake that k is equal to alpha plus j beta. The field takes this form, and now this is in time harmonic form. We can convert this to the time domain form through a real operator. And now we have the familiar looking expression of the electric field vector. Now let's consider substituting this into a form that can be used to find the magnetic field without using Maxwell's equations. We'll consider the next term as the impedance of a material. So the impedance of a material is defined as this expression. And now if we were to take the complex number of this phasor representation, it would appear as the following. And from here, if we know the propagation vector and we also know this impedance and the electric field, we can actually just directly solve for the magnetic field, assuming a plane wave solution. And from here, use similar steps as above to derive what the magnetic field is in its time form. Thank you for watching. This has been defining Maxwell's equations, or wave equations. Please check the YouTube channel for more videos on electromagnetics.